Hello calculus students. In this problem we're going to be examining exponential decay. Here you see an equation, has an e to the minus kt, so we know it's going to be exponential decay. And this equation really is an example of Newton's law of cooling. So pause the video, take a moment and read the question, and then we will begin solving it. Alright, first off we want to validate the model, so we note that if we plug in 0 for t, then k times 0 is 0, and e to the 0 is 1, so that's just simply 1, and you add those two numbers together, and you get 98.6 degrees Fahrenheit, and as you've just read, that corresponds to the living body temperature. So that is the temperature at our initial time. All right, so now let's, now that we validated the model, and that makes sense, let's solve the problem. Here's the model. We need to solve for this variable, or this parameter k, and we know that the body is cooled 2 degrees after the first hour. So at t equals 1, we lose 2 degrees. So we start out at 98.6, we lose 2 degrees, and we have 96.6 degrees. So on the one hand, t of 1 equals 96.6, as we just figured out here. On the other hand, we plug that into the equation, and then we clean this up. Now, putting this together, and then we're going to solve for that k up there, right there. So, yeah, let's just go about solving this. So we're subtracting both sides, we get 20.6. Then we're going to divide by the 22.6 and simplify. And I have to do these calculations here. So let's see here. We get 0.9115 equals e to the minus k. Then we take a natural log of both sides. And we get minus k, because natural log and exponential are inverses of each other, and we get minus 0.0927 divided by minus 1, and that is our value for k. Alright, now that we have that value, let's answer the next question. Right, now this question asks, what is the temperature when, or at what time is the temperature changing at a rate of 1 degree Fahrenheit per hour? So we have a rate of 1 degree Fahrenheit per hour, so that implies a rate of change, and that's a derivative. So we're going to differentiate this equation right here. So let's just go ahead and do that. So the derivative of 76 is 0. We factor out the constant. The derivative of the exponential function is the exponential function, but we have a linear function inside here that we have to differentiate, and we just get the coefficient. Then we simplify that, and let's see, we get t primed of t is equal to 2.1018 e to the minus 0.9 t, and now the rate is 1 degree Fahrenheit per hour, and this is the rate of temperature change, so that will be equal to 1. So we have 1 equals this expression on the right hand side, so we divide by that, and we get this number here, 927t. And then once again we take natural logs of both sides. And that works out to t is equal to 7.98 hours. So that is our solution. And now we look at the rule of thumb. So after 24 hours, we plug 24 in to get the temperature. So after 24 hours, we want to know what the temperature is. All right, so you work all that out, and you get 78.443 degrees Fahrenheit. And how does that compare to the rule of thumb? All right, well, we're starting out at 98.6 degrees Fahrenheit, and then we have to subtract. Let's see, we lose 2 degrees after the first hour, and then we lose another 1 degree for the next 23 hours, so that's 23 degrees, and that turns out to be 73.6 degrees Fahrenheit. So that's for the rule of thumb, and that is for the equation, and you notice that the equation is greater than the rule of thumb, and that makes sense because remember it took almost 8 hours to lose the degree. So the equation will give us slightly warmer temperature than the rule of thumb will. All right, good luck.